definition of capacitance. We've then kind of backed up a little bit and talked about the idea of a voltage source. Usually we kind of call that a battery or an EMF, although it doesn't have to be an actual battery. And how that produces a current. We've seen resistance, the microscopic origin of resistance, and we've seen the relationship between the voltage, the resistance, and the current, which we call Ohm's law. Again, this is the voltage form. There are other forms you'll see, but this is Ohm's law in a nutshell. And this is really the governing principle of circuits, which is what we're talking about. When you pair this up with the definition of capacitance, energy stored in a capacitor, and really that's about it. You have a robust set of equations that you can use to do a lot of work. So today we're going to talk about how to combine resistors, like we talked about how to combine capacitors, what to do if you can't combine them simply, and then hopefully by the end of the class we'll get to what happens when you have resistors and capacitors together. Okay, so just like with capacitors, you can put resistors in different arrangements. They're series and parallel, basically. The reason you're going to do that is also because, just like with capacitance, resistors are usually available in certain denominations, and you can't just create any resistance that you might need for your particular application, right? And it all boils down to voltages are usually available in certain denominations, and if you need a really small amount of current, but you only have a large voltage available to you, you've got to find a way to reduce that current. So, I mean, there are other reasons to do this, but this is one of the driving forces behind it is that you don't have an infinite supply of these values available to you. Resistors only come in certain values. Right? So, first way we can hook them up, doesn't have to be the first, I suppose, is this, which you should recognize by now as a parallel arrangement. Again, don't let the graphics fool you. People draw arrangements of resistors in all sorts of different ways. At some point that gets governed by an actual schematic and you need to show somebody how to run wires. What's going to tell you whether or not it's a series or a parallel arrangement is trace the charges, that is, trace the current. If they ever have an option, they can go left, right, straight forward. If they have a fork in the road, it's a parallel arrangement, right? If they don't, it's a series. So for this arrangement, I've drawn it parallel, this is fine, but if you're the current, trace your path along the wire, you come to this, which we'll usually call a junction. You have an option, right? You can go through any one of those three resistors, but not all three. This is by definition a parallel arrangement. A lot of times you'll see these drawn like this. You don't have to write this down if you don't want to. Right? Which just, you know, when you look at it, you're like, oh, it's just god-awful. But it's the same idea. If you're the current, you come in here and you take a right turn or a left turn, right? So this is a parallel arrangement. I'm not going to try to fool you with the graphics. You might see that in some other places. But here at the beginning of all things, right? I'm not interested in you being clever and deciphering a strange drawing. I'm interested in you understanding the physics. If you have this in your future, you'll get really good at deciphering the strange drawings as you go along. But the physics is what I'm concerned about. So I'm not going to give you stuff like this. I'm going to stick to what is obviously a parallel arrangement, like this. So we'll just get rid of that guy just as again. Remember from our discussion on capacitors, there are some things that are the same in parallel arrangements. What were they? What is the same for every component, be it a resistor or a capacitor or anything else in a parallel arrangement? Voltage. The voltage seen by the components, right? So the idea is this is connected either directly to a battery or it's a component in a larger circuit, but there's an EMF somewhere, and whatever voltage you would measure across this gap, right, between those 2 points is going to be the voltage that is seen by each one of these. So everything having to do with the voltage is the same, but everything having to do with charges are different, right? And that's because the charges that are flowing into these things, which we're now equipped to call a current, but a current is just a movement of charges, right? It has an option. So everything everything having to do with the voltage in a parallel is the same. Everything having to do with charges is different. It's the same as it was with capacitors. So, in this arrangement, we don't know the values of these resistors. Let's call this R1, R2, and R3. But assumedly, they're different values. So what we're going to find is that there will be a different amount of current flowing through each one of these. Right? But the voltage seen by all of them is the same. Why a different amount of current? Well, quite literally, current is going to follow the path of least resistance. So whichever one of these resistors is smallest, we would expect to find the largest amount of current flowing there. There will be current through all of them. You'll never have zero current in one of these legs. Although, if you have one of these resistors set high enough, it will practically be zero. It will be negligible, right? This is how measuring instruments work. We'll talk about that in a little bit. But you're always going to find some current in each one of these resistors. Sometimes it can be negligible, but probably not. If you're in an actual circuit that you're putting in some electronic device, you want current through there, so it probably will not be negligible. But the smallest resistor will have the most amount of current. The largest resistor will have the least amount of current. To handle this situation analytically, we did the same thing we did with capacitors. You actually already know how to do the math. Unfortunately, it's backwards. So if I want to know some sort of R equivalent, in other words, if this circuit is going to boil down to some other circuit that just looks like this with one resistor. And remember, when we did this for capacitors, the idea was, from the battery's perspective, there are two different arrangements which act exactly the same. The same amount of charge flows out of the battery in both arrangements. So our strategy is always to take complicated arrangements, reduce them down to simple arrangements where they are equivalent in the sense that the battery puts out the same amount of charge, or same amount of current, if you will. But they're easier to analyze. Same idea here. There is some system for which this acts just like this. And the rule is here. 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus dot, dot, dot. Right? So just like a series arrangements of capacitors, it's the same math, it's just backwards. Or I guess inverted. So in summary, for a parallel arrangement of resistors, we're going to use the inverse summation rule to find the equivalent resistance. The voltage seen by the resistors is going to be the same, but the charges, or I should say, the current flowing through each one of those will be different. All right. Switch to a more vibrant color. The other option, of course, is a series arrangement. I'll do it horizontally. Where you can tell it's a series because the charges or the current coming through have no option. It has to go through all three of them. And for that reason, we find that the current is the same. But in this case, what we're going to find is that the voltage, we will say the voltage drop across each individual resistor will be different. We saw this a little bit with capacitors. If I had 3 capacitors in series connected to a 9-volt battery, what we decided is that the voltage, after they were charged, the voltage measured across the plates of each capacitor would be different because the charge was the same, and the charge is in the definition of capacitance, right? C is equal to Q over V. So if the charge is different, the voltage has to be different if the capacitance is different. I'm sorry. If the charge is the same, the voltage had to be different. Something similar is happening here. The current flowing through each one of these is the same, but the resistances we'll assume are different. What that means is that the voltage drop across each resistor is different. Of course, just like with capacitors, it has to add up to equal the whole height of your hill, right? That's how we're thinking of a battery. If you have a 9-volt battery connected to this, the voltage drops across the resistors will be different, but the summation of them has to be 9 volts because that's as much as you have. You never get a higher hill than your battery provides to you. Okay. So the summation rule here, our equivalent is just equal to the simple sum of all. So very simple. Just like a parallel arrangement of capacitors. Again, you know how to do the math. It's just backwards. Questions so far? All right. So let's do a simple example to see how it works. And I'm going fast here because if you can handle the capacitors that we did last time, you can handle this. It's very, very, very simple. So let's do this. So I have an arrangement here. We have a 3 ohm resistor, or 2 3 ohm resistors, and 1 2 ohm resistor in this arrangement with a 9 volt battery. And I'm just going to ask you simple questions like, what is the current through each resistor? V drop across each resistor. Simple things. Well, later we'll see how to calculate things like the power that's dissipated. Just like a capacitor could be used to store energy, we're going to figure out that a resistor disperses energy, if you will. We'll see that in just a second. But if we do this, any other question I can ask you will be sort of academic. Same ideas with the capacitors. We're going to go through and draw a series of simpler circuits. The most obvious way to simplify this that I see is to combine this parallel loop into one resistor. So I'm going to redraw like this, where this is my 9 volt, this is my original 3 ohm resistor, this is the guy right here, and I've replaced this loop with one resistor. This is going to be some sort of R equivalent. I've got a parallel arrangement, so I need to do my inverse summation. I just do that on the side. 1 over 3 ohms, that's the first one, plus 1 over 2 ohms is going to equal 1 over R equivalent. Same idea. Get a common denominator, I'm pretty sure it's 6. That's going to give me 2 over 6 and 3 over 6 here, which gives me 5 over 6. Notice the ohms is still in the denominator, because that's where my resistance is. Which means if I invert that, right, this 5 over 6 is equal to 1 over R equivalent. If I invert both of them, R equivalent is going to be equal to 6/5 ohm. And the same thing is going to happen with these that happened with series capacitors, right? The series capacitor, putting capacitors in series serves to lower the capacitance. The resultant capacitance was lower than the smallest capacitor. Same thing happens here because we're using the same mathematical relationship. This equivalent resistance is smaller than the smallest resistor in the parallel arrangement, right? That's just a little over 1, it's 1.2 if you're keeping track, right? 1.2 is less than 2. So the parallel arrangement serves to lower your resistance. At any rate, this becomes 6/5 ohms. Now, I'm going to redraw this circuit. I now have a simple series. So I'm going to redraw it like this. Where this is my new R equivalent. If you want to subscript your R equivalents with 1, 2, 3 to keep track of them as you go, that's fine. You don't have to, as long as you can keep up with it and I can see what you're doing. The subscripting and bookkeeping is your business. In this case, I have a series combination, simple summation. I've got 3 ohms plus, what is it, 6/5. Common denominator is going to be 5, so I'm going to get 15 over 5 here, plus 6 over gives me 21 over 5 ohms. So that's my equivalent circuit. And the whole idea, remember, is for this circuit, the battery acts exactly like it does for this circuit. So we can now tell things about what the battery's doing and use our other physics knowledge to let that trickle down into other situations. So I want to say, okay, how much current is being produced by the battery in this situation? For that, I have Ohm's law. As applied to a particular resistor, right, this will tell you the current flowing through that particular resistor when that particular resistance, quote unquote, sees a particular voltage drop across it. In this case, what's the voltage drop across this resistor? 9 volts, right? You got one resistor, you fall the whole way down your hill with just the one resistor. So the V drop here is 9 volts. Yeah, 9 volts, that's where my battery is. So I just basically solved this for current. It's 9 volts over 21 over 5 ohms. That's going to give me 45 over 21. What is my unit here? Amps or amperes. Which is a little over 2 amps. That's pretty good amount of current. That is lethal, in case you're keeping track. All right. So now, what do I know? I know the amount of current flowing out of the battery. But from our stipulation here, which is that the battery acts exactly the same in all of these arrangements, that's what makes them equivalent. I can go back here and say, okay, well, how much current is flowing out of this battery? Well, it's 45 over 21 amps, which means how much current is flowing through this resistor? Well, it has nowhere else to go. So the current here is, what did I say, 45 over 21 amps. Has nowhere else to go. Once I do that, I can actually go ahead and calculate the voltage drop across this resistor. How do I do that? Again, I use Ohm's law. Get rid of that. Here's Ohm's law, right? A while ago, I did it for this resistor, which had a voltage drop of 9 volts. That was obvious here. Not obvious what the voltage drop is here, but now I know what the current is, right? A while ago, I used the voltage drop to find the current, but now I know the current. So I can go into that arrangement and use the current and the resistance to find the voltage drop. So the equation's already solved for what I need. Current is 45 over 21 amps. The resistance is 3 ohms. This is getting unwieldy. What's that going to be? 135 over 21. If I were doing this on paper with a calculator in front of me, I absolutely would be using decimal values here. I don't mind if you do. I also don't mind if you use fractions. I don't have a calculator with me except on my phone, so I'm just going to do the fractions. No big deal. 135 over 21 volts. So that's my V drop across this resistance. If somebody wants to pull out a calculator and tell me what that is, that would be fine with me. Your fellows might like it for it. Once I have that, it's now time to start turning my attention to the other one. Okay. So 45 over 21 amps flows through this resistor and comes into this junction. But there it splits. I have some going through the 3 ohms, some going through the 2 ohms. Where do you expect to find the most amount of current?
Small one.
Through the 2 ohm, least resistance. In this case, they're really close, right? So it's okay. It won't be an extreme difference. Somebody want to take a guess as to what the ratio of currents flowing through the top one and the bottom one will be, though? You saw the same thing with charge and capacitors. If I ask you to find the ratio of the current flowing through the top resistor to the current flowing through the bottom resistor, anybody want to take a guess what you're going to find? The way I asked it, it'd be 3 over 3 halves. But yeah, if I asked it the other way, it'd be 2 over 3. Yeah, absolutely. So this is all stuff you can use to calculate it if you want to. We'd have to take a few more steps. But it's mostly just as a sanity check. Like when you get an answer, if you find that you have more current flowing through the top one than the bottom one, that's a clue that I did something wrong. Or if you find like 7 amps here and 0.5 amps here, that's a clue you did something wrong. So it serves as a check and an intuition builder. How is this going to split up? How is it going to, go in the junction? Well, let's get back to it and see if we got it right. So first thing I would say, it would be useful to know the voltage drop across the loop, right? So I can do that from here. I know the equivalent resistance. I know the current flowing into that resistor, right? That resistor represents this loop. So I could find it there. I could also, if I'm really confident in this answer, I could subtract this from 9 volts, right? I don't really want to do that fraction, so I'm just going to recalculate it. But you can do it any way you want to. Let's find the voltage drop across that. I know flowing into that resistor is 45 over 21 amps. And that has a resistance of 6/5. That's going to be what, 9 over 1, so 54 over 21. If I did that right. Now, as a sanity check, let's add up. My total voltage drops should equal 9 volts. If I add this voltage drop to that voltage drop, what am I going to get? It's going to be 189 over 21. Yep, that works. 9 times 21 is 189. So I did it right. So, what do I know here? Well, now I know the voltage drop across here. No, I'm not going to write it there, I'm going to write it here. 54. Alright, now, that's what I calculated. Now, let's use the physics. If that's the voltage across that resistor, what's the voltage drop across each of these resistors? The same, because they're in parallel, right? So now I can write it here with confidence. Each of those resistors sees, quote unquote, 54 over 21 volts. Now I can tell how the current splits. I still have my same expression, Ohm's law. I know the voltage, I know the resistor, I don't know the current, which is what I'm looking for. Rearrange. So it's going to be 54 over 21 volts. Divided by 3 ohms. Is it 16 over 21, I think? I believe that's right. No, 18 over 21. Yep, I like that better. So that's the current flowing through the 3 ohm resistor. Which the bottom one, you can calculate, this is the same method, or you can see that there's 45 over 21 flowing into the junction. If I know that 18 over 21 is flowing through the top one, that means the bottom one is left with 28 over 20, no, 27 over 21. I did that right. Yep. Yep, 27 over 21. I just subtracted 18 over 21 from 45 over 21. If I look at the ratio of the top to the bottom, I get 18 over 27. Oh, I said it wrong a while ago. Whoever said it up here was right. Yeah, I did it backwards. The ratio of the top to the bottom is 2 over 3, not 3 over 2. I said it wrong, right? And yeah, of course I was wrong, because the most current has to be going through the least resistor. My apologies. Whoever said that, good job. So the ratio of the top one to the bottom one is 2/3. Invert the ratio of the resistances. Again, that's not how I expect you to do the problem, but it's a nice sanity check. If you understand this to the level where you can do that, rock it. The direct calculation is always available to you. Does that make some sense? There's really nothing past that as far as the simple circuits. So if you have questions, ask them now. Once you do a couple of them, it turns into no big deal. Yeah?
How did you calculate the current for the second resistor?
The 2 ohm?
Yes.
So I'm realizing 45/21 is flowing into this junction and splitting. And I directly calculated that has 18/21. So whatever's left has to be going through here. So I just subtracted my answer from the top from this. You could directly calculate it. Hopefully you get the same answer. So either way works. If you're really confident in your first answer, just subtract it. If you feel like maybe you need some self-assurance, recalculate. Good question. Other questions? I know I'm going fast, so if I lost you, speak up. You're probably not the only one. All right. Then let me get rid of some of this. Now, like I said a while ago, there are other questions I could ask you, but if you can do that, all of the other questions are basically answered for you. One thing we're going to realize is, well, not necessarily realize. I asked you last time about toasting bread and how resistance plays a role in that, right? Resistance causes something analogous to friction on the microscopic level. It's definitely not friction, but it's kind of the same idea. There's an energy exchange between the charge carriers and the atoms with which they're colliding. The energy is regained from the potential, right? Which is why batteries drain. That's why you have to replace them, because they're giving more energy as they lose it. But they don't lose it to the universe, but they could lose it to their system. Right? So that heat represents